I'm Fengsha from Almaty, and today I just want to talk about some challenges and the recent advances in trustworthy graph learning, I think. So we are all here talking about machine learning and graphs. Let's start with quite simple questions. I think you can hear this, you can see these questions now. So what is a graph? I think it's quite simple, right? I would like to invite all of you to participate in this game. You can use your mobile phone or your laptop and just scan the QR code on the top right, or just go to your browser and use the code here. So, okay. Basically, you will see one input box. You are able to enter multiple words, not just one word. You can use multiple words. I guess that you might be able to just submit once. So let's just, yes, everybody, let's have some fun. What is a graph? Because we're all here talking about machine learning and graphs, right? So what is a graph then? That's a good idea. How about we ask ChatGPT? Yes, Chat, I would reckon that ChatGPT definitely knows, but I think I would more interested in what you would say. We got 5, 7. Good. I can assure you that this Mentimeter is absolutely anonymous. So just be honest. That's fine. We already see some words here. I think some keywords that closely related to graph. Of course, as you all know, that we have nodes, we have edge, we have relationship, we have some other or entity or interactions. So of course we have network, because sometimes we call graph just network, and we see I think relationship is very important in graph. And I think I will come back on that later. So while some people are working on this, and let's just continue. So just add a few things here, because everybody knows what is a graph. But when we talk about a graph, when people are talking about a graph, you may think of this thing. It's basically a pie chart, right? Or this histogram, or even just scatter plot or box plot. So sometimes we call them graphs, but we all know that they are not the graphs that we are talking about today. So we know how to, I believe that everybody knows here how to define graph, and there are many types of graphs. Then what is graph learning? I think in my position in this regard is that there is no unified definition of graph learning yet, because we have seen a lot of terms like machine learning on graphs that in this workshop. So, or machine learning over graph, or machine learning with graph, or just a graph machine learning, or sometimes graph representation learning, or network representation learning. So, or just simply learning on graphs. So basically, we have seen a lot of such terms. And in most cases, they are exactly graph learning. So there are a few survey papers have been published in this over this recent years. I did ask ChatGPT what is graph learning, and ChatGPT told me that graph learning is a type of machine learning designed to analyze and model data that is represented in the form of a graph or network. So basically, I think that's a quite general definition of graph learning, which is okay, of course, as you can see. And ChatGPT also told me more. It talks about graph learning algorithms are designed to analyze the structure of the graph or extract useful patterns or insights from it. And it also says that it has a wide range of applications, as we all know. So another question here is, why trustworthy graph learning? So trust is important, as we all know. So basically, I use the term trustworthy graph learning because of two recent trends. And I believe that you all know. The first trend I would like to mention here is trustworthy AI. In recent years, as you can see, that there are many countries that have created their own national strategic plans in AI. So as you can see that in almost all this strategic plan, trustworthy AI is, I should say, one of the most critical things, one of the most critical need, drive, and targets. So you can see here from here that as far as we know that in Australia, we have the AI action plan, which was created just more than 1 year ago. There are quite a few models for trustworthy AI, basically. So I think just this is just one example. As we can see that trustworthy AI could be concerned about many aspects, different aspects. This slide shows us the four principles that were defined in the ethics guide for trustworthy AI in Europe, I think. On the other hand, another trend I would like to mention, as we all know here, is graph learning, of course. Over the past 5 years, we have seen a remarkable increase in the number of papers, academic papers, published in major AI conferences, as we all know, and you can feel. So talking about this ICAR, as you can see that graph neural networks, of course, is one of the major model of graph learning. For graph learning, GNN has become one of the top 3 keywords. So there are a lot of events like this workshop, and also there are many other, also there are some conference events and many other related workshops. Last year, my colleagues and I also organized one we called Graph Learning. So basically, we will organize a second edition of this workshop this year. And we are also running one special issue on graph learning of TNNLS. So we just decided to extend the deadline until the 1st of July. We all know that there have been quite a few models, or a lot of models proposed in this area. I'm not going to go deeper into any of these models, but I believe that you know all of them very well. So in regards to application, we all, I think, recognize that graph learning could have significant impact on many application domains. So as listed here, as you can see, and many others. Just a few examples. I think the first example I would like to mention is anomaly detection. Anomaly detection has been quite a hot research areas for many years, because it's really important, of course, for many domains. But we noticed that little attention has been paid to scholarly data. I mean, anomaly detection is scholarly data. With the increase of the volume of publication, and as we can see that there are a lot of scholarly data, or especially publication related data. So, and there are also many I think anomalies in those data as well, which has not been noticed yet even. In this work, it was just published, I think, quite a few months ago. So we studied the problem of anomalous citation detection. So that could be a little bit tricky anyway. I know it's hard to define what is anomalous citation. So it's really hard to define that. But I think we thought that it would be a topic that was starting. So I'm not going to go to the detail, but this is the model that we proposed. Basically, there are 4 major components here, as you can see. Basically, it's a classification task, and so the final component is logistic regression classifier, which is quite normal. So what's interesting here, I would say, is in addition to the node representation module and also the edge representation module, we introduce one module, we call it citation purpose classifier. So of course we need to extract some citation context from papers, and then we use this as what we call citation purpose to help with this anomalous citation detection. So that's basically the process for experiments. We use the Microsoft academic graph, of course, plus some other manually extracted data sets. And especially we need to artificially generate the anomalous citations. We did quite a lot of experiments, and which verify the performance, of course. So the second application is not surprising. I think we can use graph for recommendation. But as we know that we may encounter some issues or challenges in regards to, for example, the sparse data and also the cold start things. So that could be very hard to initialize the metrics. So when we do the recommendation based on metrics factorization. So here we introduce trust. That's one thing. Another thing is that we develop this framework. Actually propose two approach here. One for linear representation. Another one is for non-linear representation. And we found that our method can deal with this cold start issue or matrix initialization issue quite well. Another thing that application that I want to just maybe quickly mention here is relationship mining. We talked about the relationship earlier. So it's about advisee relationship mining from scholarly data. So we can see the authorship in publication data or metadata. However, we never know who is whose supervisor. So this work proposed to a solution for mining or discovering the advisor-advisee relationship from just simply from publication metadata. So that's the framework, and we use a lot of things that you are quite familiar, autoencoder things, and also pooling, finally is a classifier. So again, here we did the experiments based on Microsoft Academic Graph again, and also we extract some data from the academic family tree. So again, some experiments results. Then I think that's pretty much we understand that graph learning can be applied in many areas and deliver very promising performance. But as we also know that there are a lot of challenges for doing that to realize the potential of graph learning. So I want to invite you guys again to do another very quick poll. So what would be the #1 challenge in your mind for graph learning? When we do graph learning, what would be difficult for you? So I'm not talking about just write a paper, but basically if we want to implement graph learning in real world, what would be difficult? Not that easy for people. Yes, just use a mobile phone and scan the QR code, and then we will have some good scalability. Definitely, yes, that's difficult, really, because in many cases, and we have large or big graphs, I think. Real world data sets or data quantity is definitely another thing. Complexity, of course, especially graph. So we have privacy issue, which is not always, never easy. Efficiency, of course. So I think we have touched on multiple things here. Let's just move on. Again, ChatGPT told me that told me there are it listed 6 biggest challenges for trustworthy graph learning. Here, not just graph learning. I asked ChatGPT about trustworthy graph learning because we're talking about trustworthy graph learning. The first one, data quantity. Second one, interpretability, generalization, robustness, reproducibility, and ethics. So basically, we all know what these terms mean. I'm not going to explain in details, but I would like to invite you guys again to rank this topic, these challenges. What will be the #1 challenge? What would be maybe the 10th? So the #1 will be the biggest challenges, and the smallest goes to the bottom. That's how it works. Here I listed 10, just 10, based on what I have seen here. So data quantity, or you can say real world data sets. And the second one is about transparency, of course. And the third one, you can include security here, because I use the term safety, but I think it's more broader than security. So, and also we have some other ethics, privacy, and also computing platforms, especially hardware evaluation. That's also a challenge that I would like to put it here. So yeah, as we can see that there are quite a few concerns about generalization and data quality and the efficiency. Efficiency is really what I like anyway, especially due to the not increase, but due to the increased use of large models. I personally very interested in small models rather than large models. So because small models is something that I can handle, my group can handle. So okay, I think we have one winner now. Generalization is that's a little bit surprising to me anyway, but it has been important, of course. Data quantity followed by and efficiency. So just a few words about why graph learning is so challenging. Because we all know traditionally when we deal with text, audio, video, we just convert them into some simple line graph or sequence or grid graphs. And there are a lot of machine learning tools, especially deep learning tools that designed for processing those simple graphs, let's say. But the challenge is that in real world, most graphs we're talking about, they are long Euclidean. So they are due to complexity, as just mentioned by you guys. So real world relationship is so complex. So that's why most real world graphs cannot easily be processed with current machine learning or deep learning tools. That's why we need new graph learning models or methods. So I would like to showcase maybe just a few recent advances in this area very quickly. First one is about the challenge of information inequity. So as we all know that GSAM, the message passing in GSAM normally assume that the information from all labels are equally important. So that assumption is not applicable to many cases. For example, here we just focused on scale-free networks. So I think that's basically the thing motivate this work. We proposed actually 3 mechanisms to address this issue. We call our framework SenGCN. So the first mechanism we use is the label propagation. We propose to use label propagation to quantify the similarity between hub vertices. That's hub nodes and their labels. We also developed a graph transformation method to capture the influence of hub vertices by vertex centrality. So basically, that's a second one. Third one here is a hub attention mechanism. I think that's a very interesting one because we assign new ways to non-hub neighbors associated with the same hubs. So this is quite different from the general attention mechanisms used in many networks. So of course we did a lot of experiments, and actually we used, if I remember correctly, 5 data sets for 4 tasks, including node classification, clustering, link prediction, and also graph visualization. So this is just one snapshot of our algorithm, and as we can see that our SEN GSEN perform quite well, I think. Second one I just want to touch is the graph, what we call graph force learning. So is also something that I think I would be very proud of this thing, this idea. I like this idea, I should say. So the challenge here is the challenge that we try to address here is try to fully reserve the structured information when we do feature representation. So in many cases, we need to do feature representation. However, due to many, I would say many current methods that are not able to fully preserve the structured information of networks when doing this. So our idea, our basic idea is to introduce some physical law into this network representation. So this idea, I think the original idea, the first idea was published in IEEE Big Data 2020, and last year we extended this idea to attributed graph networks. So we call it attributed graph force learning. So, but here I think I mainly talk about the original idea here. The idea is basically simple. We just introduce the spring electrical model. Spring electrical model actually, as you know, that describes the motion of particles under force. So we define the relationship between nodes or vertices as using this model. So each of the relationship will have a attractive component and also another repulsive component. So just like a force, the force law from physics. So we call our this framework G-force. So what we found finally is that this approach has quite a good, I think, advantages, which is really good is scalability. So this, I think, we mentioned this just in the previous slide. So scalability is very important, but I think we actually didn't expect this at the first instance, but it comes out that this approach has such a good advantage. I think it could scale very well to large networks. Again, just a snapshot of the experimental results, and which is good, I think. Another challenge is how to explore the, let's say, multivariant relationship between vertices, between nodes. So real world, especially in real world, many relationship is not just a binary or pairwise, and it could be multivariant. So it could be more complex than just a simple link. So there could be multiple link, and could be, as we use the term, is multivariant. So, but how to explore such information, and many of such information could be lost by many existing methods. So I think that's the motivation for this work we have done. This work was done quite I think a few years ago, basically, but I think it's still interesting to talk a little bit about it. So of course we proposed a solution to do this multivariate relationships aggregation, and basically that's the structure, which is not that difficult to understand. We did this for classification task. So this framework, I think, particularly designed for a classification task. And we found that our approach consumes much less training time. So that's another issue that we're trying to address during this work. So some results I will give this. So I think in this part, I would like just to mention maybe two open challenge. The first one is graph anomaly detection. So very recently, we published one survey paper on this topic, but we call it graph learning for anomaly analytics. So if you're interested in, just check it out. We all know that graph anomaly detection could be useful for many applications as listed here. So I'm not going to read this out. And there are also a lot of challenges in this area. Another area I would like to draw attention is graph lifelong learning. Yet another survey paper, let's say, survey paper, yes, published in IEEE Computational Intelligence magazine. So basically, every graph is evolving, and when we deal with real world graphs, we need to keep this in mind, and we have to develop some lifelong learning mechanisms to deal with dynamics in graphs. So which is not easy, of course, never easy. So you need to deal with the model efficiency, robustness, and many other things, of course. So finally, some takeaway messages, I think. The first message is that graph learning is very hard, of course. And the second message is that trust is essential or is important or critical in graph learning. So that's why I call it trustworthy graph learning here. But it's never easy to realize, to especially implement trustworthy graph learning in real world. There are a lot of open issues here in this area, and there are a lot of opportunities because this area, I think, covers multiple disciplines. So it would be a good chance for us to do some interdisciplinary collaboration here. And also, if you're interested, don't forget to submit to our DTNS special issue on graph learning. So this bar chart was from a course I taught just days ago, early this week, because that's feedback from my students. I asked how much will you trust ChatGPT, because trust is important, as I said here. So as we can see that I think the majority of people are quite I think is just give ChatGPT some moderate trust. I should say so, which is of course not surprising. Some references and yes. Thank you. I think I'm ready to take some comments or questions.
Thanks, Feng. Do you have any questions from the audience? All right, I will lead once more. So Feng, first of all, thank you for the talk, and I appreciate the engaging polls in the middle. So I was kind of curious, like, you know, a lot of the talk seemed to focus on these themes of trustworthiness. Are you, do you have any kind of like ideas on which of the disciplines in the graph learning domains you think are most specifically warranting trust. For example, you talked about some domains like Rexis and citation networks and scholarly networks. But do you feel like there's a particular subfield or application domain in which you feel like trust is far more important for graph learning systems compared to others?
Yes, that's a very, very good question, and it's not an easy one. I think it's a big question anyway. So because I don't know every discipline, I don't know every domain, but what I think when you ask this question, and what I come to in my mind is what I become very interesting is exactly health or brain networks. So basically, I just started, I think, reading something around brain networks and brain-related disease. So in that domain, I believe trustworthy is really important because it's about our health, our life, even. So and of course, there are many other safety critical applications or domains in which I believe that trust between, especially, I think trust from, let's say, from human would be very important. So yes, but of course, establishing trust is a long process, and especially when we talk about human and machine. So that's why I pose this question to our students: how much you would trust ChatGPT? Actually, in here, I'm quite interested to ask how much you would trust graph learning or even machine learning things in general. Basically, it's never easy to build trust between humans. So I think it'll be much harder to build such trust between human and machines. That could be happening in almost every domain, I would say.
Thank you. Any more questions? Okay, one more from me. So I guess, as someone who's been working on machine learning for a long time, I think most of us would probably agree that, there's kind of these fundamental principles of ML systems, which are kind of a garbage in, garbage out. And so, people ask these same kinds of questions about fairness and other properties like robustness, for example, of algorithms. But, trustworthiness, there's an argument to be made that, and I think your poll, well, at least one of the polls, showed that data quality was a super high priority issue that many of the folks in this room think is valuable. I noticed that a lot of your work on trustworthiness also focused on like algorithmic aspects. So basically trying to correct this, in the models that we build. Do you believe that like there is actually a fairly significant opportunity, or do you think there's a good argument to be made that most of the work in trustworthiness should actually be in the data quality space, or the kind of like filtering or upstream pre-processing phase compared to, or potentially even post-processing phase compared to the core algorithmic model design?
So I would say I would personally agree partially. I think that's a big part. I would agree. So basically, I also work in data related things, and I believe that many useful models or systems are based on useful or trustworthy data, or let's say high quality data. So without high quality data, I think, as we all know, that there would be no useful systems exist. So and so that's why data quantity things or data related trust could be, let's say, more important than algorithm itself. I'm not saying this this is true in every under every circumstances, but basically, in many cases, as we see that the performance of the system could be largely depend on not just the algorithm that we design, but on the data quantity, the data. I would not say the volume of the data, but basically the quantity of the data could be the key issue that will affect the fundamental performance of the system. I think that's really one important thing, even as we, I think as we have more and more data, but unfortunately, as we see the quantity of data may not improve as the volume of data or the size of data. The size of data is expanding just so quickly, but the quantity of data but may be degraded in many cases due to, for example, many fake things. So I think you just mentioned a very, very important aspect. And but of course, I'm not saying that algorithm is not important. Algorithm, of course, we need to develop some algorithms that we can trust, of course. But the data that we use to train the model, we use to even develop the model itself could be I think something that playing a more important role. That's my
Thanks,
position.
Yeah, I appreciate the comprehensive answer.